All right, let's get right into it. Have you ever been outside and noticed how the wind feels, well, kind of chaotic? It's gusting, it's swirling all around you, but then you look up and the clouds are just cruising by thousands of feet up in this smooth, steady line. Turns out there's a really good reason for that. The wind down here on the ground is playing a totally different game than the wind high up in the atmosphere. And that difference, it's what creates pretty much all the weather we experience. And that brings us to the big question, the real mystery we're tackling. I mean, basic physics tells us that air should move from a spot with high pressure to a spot with low pressure. Simple, right? It should just be a straight shot. But it doesn't do that, not even close. So what's going on down here at the surface that's messing everything up? Well, the main culprit, the big spoiler alert here, is friction. Yep, good old friction. It's the force that really only matters in the first couple of kilometers above our heads. The ground itself, the surface of the Earth, literally puts a drag on the air moving over it. And that one simple fact changes everything about how wind behaves. Okay, so what's a good way to picture this? Imagine a snow fence you'd see on the side of a highway. Its job isn't to be a solid wall, right? It's not there to stop the wind completely. It's just there to slow it down. And as that wind slows, it drops all the snow it was carrying, and you get that big pileup. Well, the Earth's surface, with all its trees, its buildings, its mountains, it's basically a giant snow fence for the atmosphere. So when we talk about friction in meteorology, that's all we mean. It's just a force that resists the air's motion as it scoots across the planet. But here's the key part. It's not the same everywhere. A really smooth ocean surface creates way less friction than, say, a rugged mountain range. And that little detail is super important. And you can see just how big of a difference that roughness makes right here. Over a smooth surface like water, friction is pretty low. The wind only gets nudged about 10 to 20 degrees across those lines of equal pressure, what we call isobars, and it keeps about 2/3 of its potential speed. But over rugged terrain, whoa, friction is so high that the wind can get knocked off course by up to 45 degrees, and its speed can literally get cut in half. The landscape itself is steering and braking the wind. So this all sets up this fascinating sort of tug-of-war between three major forces. You see, high up in the atmosphere, two of these forces are in this perfect, elegant balance. But down here, near the surface, friction comes along and just crashes the party, tilting that balance completely out of whack. Okay, let's walk through this, step by step. First up, you've got the pressure gradient force. That's the engine, always trying to push air in a straight line from high pressure to low pressure. Now, way up high where there's no friction, the Coriolis force, which is just an effect of the Earth spinning, pulls the wind to the right until it's flowing perfectly parallel to the isobars. That's the perfect balance. But then, step 3, friction jumps into the fray. It slows the wind down, and here's the absolute kicker. The Coriolis force is tied to wind speed, so a slower wind means a weaker Coriolis force. Suddenly, the tug-of-war is totally lopsided. The pressure gradient force wins, and it starts pulling the wind across the isobars toward that low-pressure center. And that is why surface winds don't blow in a nice straight line. So what does this tilted tug-of-war actually look like on a grand scale? Well, it creates those massive swirling patterns of high and low pressure that you see on every single weather map you've ever looked at. We're talking about cyclones and anticyclones. This table lays it all out for us perfectly, at least for the Northern Hemisphere. For a low-pressure system, a cyclone, that broken balance we were just talking about makes the wind flow inward and spin counterclockwise. The result is a net piling up of air, which we call convergence. For a high-pressure system, an anticyclone, it's the exact opposite. The wind flows outward and clockwise, creating a net outflow of air we call divergence. Let's zoom in on that cyclone. Because that pressure gradient force is winning the tug-of-war, it's constantly pulling air toward the low-pressure center. The Coriolis effect is still there, just weaker, so it gives the whole system that classic counterclockwise spin. The end result is this massive inward spiral. All of this air is converging. It's all coming together, right at the center of the low. And the anticyclone? It's basically a mirror image. The wind is starting at the high-pressure center and trying to move away. Friction slows it down, weakening the Coriolis effect and causing it to spiral outward with a clockwise rotation. All the air is diverging. It's moving away from the center. Which brings us to one final, really cool thought. We've just established that in a cyclone, friction causes a ton of air to spiral inward and converge, right? It's all piling up in the middle. So, where does it go?
It can't just vanish, it has to go somewhere. And the answer to that question is the key to understanding why low pressure systems almost always mean clouds, rain, and storms.